Okay, I think we're good to go. So I'm going to kick off the meeting with an introduction of our speakers today. Tim Higgins is a celebrity. Many of you probably know Tim through smallnetbuilder.com and all the testing he's been doing and publishing results. And I have the honor of knowing Tim going way back to the early 80s when I joined Teradyne. Tim was an engineering manager there, one of the best ones we had. And then he moved on, and so for almost 20 years he has been setting the standard for test, analysis and review of consumer Wi-Fi and other networking products. So you're all familiar with his SmallNet Builder website. His work has been cited by Bloomberg Business, USA Today, Wall Street Journal, New York Times, Computer World, Forbes, and other leading publications. We're delighted to have him here. Our next speaker is Dennis Bland. Dennis is president of DB Performance, and he's been involved in WLAN technology since 2001. So that's going way back to the basically the birth of it, with 10 years of WLAN fast roaming and security experience. Dennis participated in the IEEE 802.11e and Wi-Fi Alliance WPS working groups, collaborated with Cisco in implementing CCX test plans, deployed the IEEE 802.11k VNR, and we're getting a lot of requests finally for these specifications, even though they've been around since the early days. So he's getting requests for this software and performance test, and recently released IEEE 1609 security stack for automotive applications for DSRC. Prior to DB Performance, Dennis worked in both hardware and software development roles at DeviceScape, Wind River, and Nortel. Dennis is the sole inventor of 3 patents and has designed resonant cavity antennas and wide bandwidth HDTV antennas as a side hobby, nice hobby. Okay, our next presenter is Craig Smith of .11 Labs. He is one of the Wi-Fi pioneers. He's been working with Wi-Fi back when the 11B was cutting-edge technology, and I remember that time because I worked with 2 megabit per second Wi-Fi, and I was delighted to be able to do email in front of my TV rather than be tethered to the desktop. So it was early days. And Craig's career includes wireless companies such as Intersil, 2Wire, Airgain, and Xeris. And in 2016, Craig founded .11 Labs, which specializes in Wi-Fi performance testing and offers a unique set of OpenAir and octoBox test services. So the interesting perspective Craig brings to this event is that he's actually compared and was able to correlate some of the very complex tests in the test house, and in the octoBox. And he'll explain how he did it. Last but not least, Lee Chinitz is our CTO. He is a PhD, has worked in the wireless and data communications field since 1993 with companies including Casa Systems, Cisco, and Motorola, and others. Prior to joining octoScope, he was a wireless strategist at Casa CTO office. Lee joined Casa from Cisco, where he was a Wi-Fi advanced services solution architect. His background includes Wi-Fi, UMTS, CDMA, femtocell, small cells, and regulatory work at the FCC. He is a frequent speaker at industry conferences and a contributor to the Wi-Fi Alliance, IEEE, TIA, and ITU standards development. Lee has a BS in physics from Yale, a PhD and an MBA, and he holds 20 patents. So welcome, Lee. You're going to kick us off. Let me put up your slides.
All right. Thanks, Fanny. Welcome, everybody, both here and online. So I'm going to kick this off. As you know, we're talking about mesh and roaming. We're talking about in the context of the octoBox, octoScope. octoBox, I don't know about everybody's background here, so part of what I'm going to do is to bring everybody up to at least some level of understanding of what it is that octoScope does and what an octoBox test system is. And we'll talk a little bit more about what we can do, but leave some of the really detailed things to the experts that Fanny just introduced. So we always start off when we try and describe what we do here at octoScope by talking about how wireless testing has usually been done, or is often done, even now, right? So there's kind of two main ways, maybe three, but talk about these two that people do wireless testing. One is using large shielded anechoic chambers. These have pros and cons. Pros are they're well shielded. They're you don't have interference issues. It's pretty easy to get nice reproducible results, but they're big, they're expensive, they're hard to use, and you often can't get more than one, if that. The other one that people do is walk testing in real-world environments. Again, pros and cons. Pros there would be that you do get a sense of how environments are working in the real world. You can do things like look at rate versus range, which can be difficult to do in a chamber. But again, the cons are here that you're very susceptible to external interference. It's hard to get reproducible results. And when you see behavior of the product that you would like to understand a little bit better, it's very difficult to get back and see it again, right? Because it's hard to get exactly the same conditions if you're out kind of in an open air environment. So, we come at this by saying, so what if we could kind of have the best of both worlds? Best of both worlds would mean, a system that is shielded from external interference, that allows you to measure performance versus range, so rate and other things versus range, that lets you model a real world environment in terms of things like interference and multipath. But that gives you very reproducible results, so you can get back to seeing behaviors that you might want to investigate more closely, and that are fairly easy to use and inexpensive. The way we do that is by the use of these shielded environments, which you can see all around you in the room, and we'll see a lot more of that throughout the day. We use programmable attenuation in order to model range. We have other test instruments that let us, for example, emulate multipath, that let us generate controlled interference. And again, the whole thing is fairly simple, easy to use, and gets you highly repeatable results. So that's the octoBox. This is a kind of a standard kind of configuration. That's what things look like. If you look around the room, you'll see them in other configurations, and you'll see many other configurations during the day. But the basic idea here is that it lets you set up tests that are like the kinds of things I just described, and lets you go from doing testing, which, for example, in a walk or drive test environment might take you hours or days, or days or weeks, and pulls that down to hours or less. You are in a fairly confined space, so from a performance point of view, you're able to see the maximum performance of the devices. So when we're talking about Wi-Fi, for example, we can routinely in our systems get to maximum MCS, so the highest achievable data rates for the technology, but then by impairing the channel, you can then see how the performance would degrade. And it lets you also emulate real-world environment, as I mentioned, with things like controlled interference. One of the devices that you'll hear a lot about today, so I just want to make sure everybody knows what it is something we call the PAL. Doesn't mean anything other than friend. And it is a test instrument. It's widely used by people who do tests. It's used by the speakers who'll be speaking today. It is a Wi-Fi device that can do a lot of different things. It can act as an access point. If you're testing a station, it can act as a station if you're testing an access point. It can also act as a sniffer, so it can be a packet sniffer. You'll see quite a bit of that today. It can be a monitor. It can also act as multiple stations, so it's a highly sort of configurable and useful device in testing. The one I just showed you is our current version of the PAL, and just for FYI, we are currently developing our next generation of the PAL that's known as the Super PAL. That's an 11AX device, and it has quite a bit of technology in it, in addition to like one of our current PALs. They're 4x4 Wave 2 11AC devices. These will have actually 3 separate radios in them. So acting as two 5 gigahertz, one 2.4 gigahertz, up to 11AX devices. In addition, they also have Bluetooth and thread capability, so that we can start using the PAL from kind of an IoT point of view. High level, where octoScope sits in the industry, we Anybody doing Wi-Fi testing can make use of the systems that we have. So we've sort of crossed the whole range of the industry, all the way from chipset vendors who are find it useful, especially in the early stages of development, through the equipment vendors, out to the operators who use it from a deployment point of view. They like to understand how their products are going to behave when they're deployed in the field. And then, the fourth one is the labs category that I have here, and speakers that you'll see here today fall in that category. You've already been introduced to SmallNet Builder and .11 Labs. So then, again, at a high level, what we do is we allow people to set up tests where you can test the parameters that are kind of shown on the left-hand side, things like throughput and roaming behavior, data rate adaptation, et cetera, as a function of changing the channel by affecting, for example, the range of the devices, the interference that they're experiencing, the channel width, motion, and you'll see some of that today. You see quite a bit of motion today when we talk about emulating motion, and I'll get into that a little bit so you understand what I mean there. But even though the system is small and static, we already talked about the fact that we have the programmable attenuation that lets you change the distance. By using multiple attenuators, you can actually emulate distance. So you can emulate a device moving around, and you'll see how that's done in some of the examples today. So we do a lot of different test applications that are sort of covered here. This is what the inside of one of these looks like. For the people here in the room, you can go around later today, during lunch especially, and take a look inside. You can see what all this stuff looks like. But this is the inside. You can see that the box is Anechoic. It's lined with foam to reduce all the reflections off of the surfaces. There's a turntable that's used to be able to rotate the device under test, and that helps you from the point of view of averaging out your results and kind of having less susceptibility to position effects or orientation effects. All of the other fixtures in here are plastic, and you can see mounted on the walls are our high gain test antennas. We have a variety of antennas. They're used for different things. So, LTE antennas or dipole antennas. What we're showing here are the high gain ones. So that's at a high level. And now I want to kind of get into the topic of the day. I can kind of imagine people saying, yeah, that sounds great. You have these little things and you can kind of do sort of simplified testing. But, what if you have kind of more complicated topologies, which is what people are really interested in these days, sort of complicated, multi-access point tests, or, you want to be able to test a whole house or something like that. So, what we say is absolutely, we have a lot of customers that use our system to emulate extremely complicated systems. So, boxes or systems like this one, and you can kind of see some of that going on in the room today. Systems like this one, or this one, or even this one. And this is a customer that actually is modeling an entire home. So each of these boxes is a separate room in the home. There's a residential gateway in there somewhere. All of the rooms are connected together via variable attenuation, so you can change the topology of the home. And flow traffic from gateway to room to room, inject interference. So you can do very, very complicated scenarios. Part of the reason that that's interesting kind of gets to the point of our conversation today, which is about sort of mesh testing and roaming. So interest in mesh system testing has really not been higher than it is right now. We're seeing a lot of interest in mesh. And the question you might ask is, why is that? And the reason, I think, is that kind of the old days of sort of pretty good enough wireless coverage where Fanny could do her email on her couch isn't enough anymore. And the reason is that kind of everything has become wireless at this point, and people care about where coverage is, so it has to be everywhere. And the way that a lot of operators are advising their customers to do that is by use of extenders and mesh products and things like that. A lot of them out on the market. There's probably more than this, but these are some of the big ones. So meshing, what's it all about, right? So there's a couple ways that that mesh systems can be put together. There's Ethernet backhaul, in which all the devices are connected to the wired connection. That's sort of a traditional wireless LAN. But from a mesh point of view, you tend to have one device that is attached to the Ethernet, that's kind of attached to the world, that is referred to often as the root, and then a bunch of other devices that are used to provide coverage, but are connected via wireless mesh links. There are a lot of different ways that those can be put together, a lot of different topologies. This is, linear topology, where you've got, let's say, one root, and then everybody else connects through in a line. There's star, where everybody's connected back to the root. There's, really full meshes in which all the devices connect to each other. One of those would be a root. And so in a 4-node mesh, we'd have something like this, where the device on the lower right there is our root node. So you can see he's connected to the world. All the other devices are connected to all the other nodes. And a client can move around and can attach to any of those devices. And then the question is, how will the data then get back to the root and back to the world? The interesting thing is that in an octoBox system, the way you would set up something like that would look something like this. And we'll actually show you this setup. In fact, it's in the back room, and you can all go and look at it. But a 4-node mesh that can do exactly what I just described looks like this. So you see we have a root node here. We have the other mesh nodes. All of the nodes are connected via variable attenuators. And so when you change those attenuators, you can essentially move the devices further and closer to each other. And the PAL that I described to you before, shown in the upper left, you can sort of ignore the other PALs right now. We would use those in this situation just for sniffing or monitoring the system. But the PAL on the far left there, he's connected to each of the boxes, and there are variable attenuators that connect that PAL to each one of those boxes. And depending on the setting of the attenuator, that PAL is either close to this one, close to this one, close to this one. And by modifying the attenuation, you can actually move the PAL from box to box. So that's kind of how mobility is done. And this is how you would set up, say, a full node, a 4-node full mesh system. But the interesting thing is that when you use the attenuators, you can actually set those attenuations to get any of those topologies that I described. So for example, a string of pearls looks like this. What I've done is I've kind of grayed out the lines where the attenuators are just set to their maximum value, essentially killing that link. And so the ones that are shown highlighted in red have lower attenuation, so that link is alive. And as you can see, in this case, root is connected to 3, 3 is connected to 2, 2 is connected to 1. And you can actually change the topology just by changing the attenuators. You do not have to go and recable things and say, now I want to set up this system, or now I want to set up that system. So kind of highly flexible. That's what a string of pearls would look like. A star would just look like this. As you can see, the root is connected to everything, but nothing's connected to anything else. A partial mesh looks like this, where the only link that doesn't exist is the one from 1 to 3. So we can set up all kinds of mesh topologies using the system, and we can do all kinds of tests. These would be some examples. So for example, we can configure the path losses, as I mentioned before, and have the mesh configure itself however it would configure it, and look at how, for example, throughput would be affected by kind of different configurations of the mesh. And this is actually a test we're going to do pretty soon here. I'll show you this one. But the idea here is, again, you can set this up as a string of pearls, and you can look at how throughput changes as you. So on the lower left hand there, I have a server. And that's connected to my root, so that's the source of my traffic. And then all the red lines are the things that are sort of active in here. And so we're having traffic that would come and be received after hopping through to one of our mesh nodes. So it's a one-hop mesh. And we can look at throughput there. We could then kind of reconfigure so that we have a 2-hop mesh and take a look at that traffic there. And we can do 3-hop mesh, so we can look at throughput as a function of hops. All sorts of different behaviors. Other kind of mesh-like and roaming-like capabilities would be tests that are related to, for example, to band steering. So for example, in this case, we have our PAL, the one I mentioned before, and you can see via the red line, it's connected here to the device number 4 there on the bottom. And we can associate that to the 5 gigahertz channel. We can then change the variable attenuation on that PAL so that it is effectively moving further away from 4. And we can watch to see the transition, for example, from the 5 gigahertz band to the 2.4 gigahertz band. We can use our PAL as a sniffer to watch that happen. So this is sort of a typical simplified band steering test that can be done. We can do load balancing tests that look something like this, where if you just look at the red lines here, you can see I've got a bunch of client devices, and I've associated them all to my AP there on the bottom, number 4. I can then provide an equally good path up to AP number 1 here. And I can even, if I want to generate additional traffic using that green PAL on the bottom there, into AP number 4. So really start loading up AP number 4, and then we can actually watch to see whether or not AP number 4 will be able to do any sort of load balancing, pushing clients off to AP number 1. So that's a kind of a quick overview of what we do, what we have, the kinds of things we can do. I want to do a quick demo of some basic capabilities. But this is a tool that we have that actually lets you emulate mobility between devices. And so, as I said, if you imagine that PAL that's connected to all of the boxes, and then you connect it, into one box, and then slowly raise the attenuation so that it's moving further and further from that box, but at the same time, slowly decrease the attenuation on another box. That's essentially the PAL moving far from one AP and close to another AP. This tool does that automatically for you. You can see it does what we call cross-ramping. So you see attenuation number 1, attenuation number 2. You can set your ramp speed, which essentially is your walking speed. So you can look at roaming tests as somebody sprints from place to place or slowly ambles from place to place. And you'll see that later on. And then what I want to show you now, or the demo we're actually going to do for you, is the one I mentioned before, showing you kind of a basic throughput versus hop test. So we're going to use that that configuration I mentioned before. There's a stack that looks not exactly like this, but pretty much like this, as I said, in the back room. Feel free to take a look at it, those of you who are here in the room. And what we're going to do is we're going to, we have it set up this way, and what we're going to do is show you what it looks like if we generate traffic from that server directly to the PAL. So you can see in this case there's no hops. We'll then move the PAL up to device number 2, and that'll be a 1-hop mesh. And then we're going to move the PAL up to the top AP here, and that'll be a 2-hop mesh. So I'm going to bring in Tuan Chen to do that demo for you.
So what I just did right now is add a remote desktop to our system over there for the back system that's on a 4-node mesh. And I'm going to show you a 4-node mesh demo for 2-hop, 1-hop, and root node, which is 0 hops. So for that, I have it set up right here for a 2-hop test in the beginning. And for 2 hops, I have the PAL pointed to node number 1 and connected to node number 1. And we have a multi-attenuator control here, which I'm using to control the attenuators, since we have so many. And these right attenuators here corresponds to the attenuators on the right-hand side here. And the left-hand side attenuators are corresponding to the left-hand side attenuators in the diagram. So what I just did is I set the attenuators already. It's pre-set up, so that way the PAL is going to do a 2-hop test, because the path you can see is highlighted in red. So I'm going to go to our octoBox software suite and clear up the previous run. And I can show you the PAL is associated to node number 1. You can see the BSS ID is 235F. And inside our diagram, 235F corresponds to node 1 right here. Sorry. So I'm going to go down and run the test and run throughput so you can see what the throughput looks like with 2 hops. For 2 hops, this is the throughput right here. You're getting roughly about 350, 400. And this is the 2-hop test. So once the throughput's done, I'm going to go back to our PAL, a multi-quad attenuator, and I'm going to go to do a one-hop test. So I'm going to move the PAL from node 1 to node 2, keeping the paths the same. I'm just going to move the PAL associated to node 2 and run throughput, and we should see one-hop throughput. So I'm going to go back and get the BSS ID of the one-hop, which is 36D6. I'm going to copy it, and I'm going to go back to our multi-quad attenuator. What I'm doing is moving the PAL here, so I'm going to max out this attenuator, zero out this one, which is for the second node. So I'm going to apply it, go to our PAL's UI, change the BSS ID, and right when I change it, I'm going to go back and click on the restart button. What I did is just change the PAL's radio interface to reassociate back to that node number 2 BSS ID. So right when it's associated, I'm going to start the throughput, and you can see the throughput of a one-hop test. And it should be associated. We can see it. There's a message associated here. I'm going to go back to our octoBox software suite, click on Run. And right when I click Run, you can see this is the one-hop throughput right here. This is with one-hop throughput. So after this is done, I'm going to move the PAL to the root node. That way we can show you a no-hop, which is directly throughput on the root itself. So for that, I'm just going to go and move the PAL from node number 2 to this path here to root node and run the throughput as well. So I'm going to go back to our multi-quad attenuator control. What I'm going to do is max out this attenuator and zero out this one, which will move the PAL to the root node. And I'm going to get the BSS ID of the root node, FCD9. Copy it. You can see FCD9 corresponds to the root node. I'm going to go back to our PAL's UI, change the BSS so it can associate to the root node only, and apply it. Right when I click apply, it's just doing the same thing. It's going to create the radio interface and associate the PAL to the root node's BSS ID. So there it is. It's associating, scanning for it. And once it's associated, the message should pop here for associated, which it's associated right now. Go back to our octoBox software suite, click Run. So right when I click Run, you can see with the no hop, this is with the root node's throughput right here. That's on top. That's running right here. This is the root node's throughput. So along with that is that I'm going to demo our PAL's monitoring capabilities. So that way when I put the PAL in monitor mode, right now it's in the root node. So I'm going to go back to our PAL's UI, go to Monitor tab, and start monitoring on channel 36 with the root node. And I'm going to mesh up the whole, I'm going to mesh up everything. Yeah, I'll change that. So I'm going to mesh up everything to show you that everything, we can see the whole mesh network. So this is apply. Go back and set this to 80 meters bandwidth. Restart the PALs in monitor mode. And right when I meshed up everything, once the PAL becomes monitor mode, you can see all of the 4 nodes. So once the PAL is up, there it is. You can see all 4 nodes. And the node that's strongest is the root node, as you can see, because the PAL is directly pointed in the root node. And also, they're about only 20 dBs off, so they're like right next to each other. It looks like the APs are right next to each other. So I'm going to now unmesh everything, and we should only see one BSS ID, which is the root node. So what I'm doing is unmeshing these attenuators on the right, on the diagram right here. It is all these attenuators. I'm going to set to the highest attenuation so I can unmesh everything. So I'm going to go back to my multi-quad attenuator control, set all the attenuators to max. And right when I set it to max and click apply, we should see all of the other 3 nodes disappear from the PAL's monitor and only see one BSS ID. So I applied it, go back to the PAL UI. As you see, these have all disappeared, and we only see one node, which is the root node.
When we draw our pictures, in order to avoid like having way too many things for people to understand, all these kind of heavy things are quads. So actually, if you look at the devices there, you'll see like this attenuator is actually 4 attenuators.
Yes.
This is actually, when we see our things, it's actually 4 antennas in a sort of an array. Or you can move them around. There's 4 lines here. There's 4 actual RF cables and all these things. So yeah. The question that's being asked is what's causing the throughput difference in the 0, 1, and 2 hop cases, right? So I mean, in the 0 case, of course, you're seeing kind of what you'd expect from a
direct connection
2x2 MIMO at 80 megahertz. In a 1 radio mesh, what people used to do before, right? Then you'd get the throughput cut in half, because the radio had to spend half of its time on the front side and half of its time on the back side, right? So you just had a timing issue, right? I mean, amount of time that you were on the air. Here, I mean, I think there is just a certain amount of overhead involved in the.
You're talking about one hop.
Yeah. Well, that would be in a single radio case. In this case, we don't have a single radio case. We have 1 radio on the front side here and a different radio on the back side. But it still has to take those packets in and then put them back out again. Okay, so I am going to, just to cover a couple of items that you'll hear about that are new for octoScope, but you'll hear them talked about today. So I want to give you a little bit of background so that you know what we're talking about. So one thing you'll hear mentioned is something we're calling the smart box. Hopefully you've gotten enough of an introduction to how the octoScope systems work to recognize that we have these shielded environments, and then we have all these devices like the PAL that I mentioned, or interference generation, that sort of thing. And if you look around here, for those of you in the room, and you look at the boxes, you'll see those devices attached on the outside coming into the box and being able to access what's going on inside via the internal antennas. So that often uses up a certain number of our ports for just for the test tools, making it difficult to scale to even larger systems. I was explaining before how we have these sort of more and more complicated systems people want to test. So the smart box is something that was recently developed by us, and it has essentially, it's one of these, shielded environments, but it has built-in test tools in it. And so, just imagine, you don't really have to imagine it, but you have a, kind of a box like the one we've got here, but then the PALs, for example, that I mentioned, or interference generation embedded directly in the box itself. So, it looks, something like this, where, again, in a previous incarnation of a picture like this, all those devices, those PALs and the iGens would all be on the outside of the box and connected inside. Now we've built our box like this, where we've actually taken those devices, put them on a plate, inserted them into the box itself. So here it is, sort of installed in the box, and here's what the box looks like. That's a smart box, but the floor underneath that box has all of that kind of built-in test tool functionality. And if you look on the left side of the box, you'll see a couple of dipole antennas, or actually 3 dipole antennas hanging there, maybe 4, and those are connected to the smart box test tools. So you'll hear about that. And you'll also hear people mention something we call Synchro Sniffer. So Synchro Sniffer is some software capability that we've been developing, and the reason for that is that, again, with these more complicated and complex test environments, we're finding that it's necessary to be able to do packet sniffing in multiple places, especially when you're looking at roaming and you want to look at watch a device, for example, as it's connected to one AP and one band, and it roams to another AP on another band and that kind of thing, and you'd like to kind of be able to see what's going on and kind of match up traces. What has been done in the past is to take multiple sniffer traces and then have to go in and kind of manually figure out which packets correlate with other packets and kind of manually line those things up. What Synchro Sniffing does is it uses an external timing source. Here I'm showing 1588, so Precision Time Protocol. We can also use NTP to time align these probes. We capture all of the sniffing using multiple probes, but then the Synchro Sniffing software will pull all that stuff together and put it into a single combined sniffer trace, and will actually identify in that trace which probe the packet came from. So we'll get automatically a set of synchronized and combined sniffing traces using the Synchro Sniffer. And so again, as I mentioned before, what you'll see some of this as well today. When you have these kind of combined traces, you can then start looking very quickly at interesting roaming meshing behavior. So in this case, we can very quickly watch a device follow it as it goes from mesh node 1 to mesh node 2, mesh node 1 on the 2.4 gigahertz band, 2 on the 5 gigahertz band. So you can see all of that happening very quickly and easily. And you'll see this actually demonstrated in real time today.